right, thanks for joining us. We're really excited to tell you about Mina zkApps, built on the Mina Protocol, which is a layer 1 blockchain focused on zero knowledge, with zkApps smart contracts and a zkBridge to interact with Ethereum and other blockchains. Today we have a few presenters. Myself, I work at O1 Labs. I'm a PM for zkApps. We have Evan Shapiro, the CEO of Mina Foundation, who will talk about the zkBridge. And then we have Brandon Kase, an architect engineer at O1 Labs, who's going to talk about SnarkyJS, walk through a hello world, and give some more info to help people get going. Okay, let's talk about architecture. As mentioned, Mina is a layer 1 blockchain. Our mainnet was launched March 2021. The big difference with Mina is whereas other blockchains are large and increasing in size as new blocks are mined. For instance, Bitcoin is 402 gigabytes in size and Ethereum is over 1 terabyte. Mina remains a fixed 22 kilobytes in size. All you need is this one zero knowledge proof to verify the entire history of the chain. We call this a succinct blockchain. Using recursive zk snarks, the current state of the blockchain can be compressed into a single zk snark, letting anyone instantly sync the blockchain with the security of a full node. An enormous amount of research has gone into zk snarks lately, both inside our company and across the industry. And our cryptography team at O1 Labs has created a zk snark we call Kimchi, which is setupless, efficient, and extensible, and it's based on Plonk 15. And you might be wondering, if we have a 22 kilobyte blockchain, how do block explorers query this historic transaction data? We have a type of node as one of the many nodes in our network called an archive node. And block explorers can query the historic data through that. But you don't need any of that data to verify the actual chain and the consensus of it. And so with Mina based on zk snarks, we had an opportunity to re-envision the design of a smart contracting platform. So let's talk about how zkApps work. As a point of reference, let's look at Ethereum Dapps. So at ETHAmsterdam, I'm sure most people are familiar with this. On Ethereum, smart contracts execute on-chain. Users send a transaction specifying a method and data arguments, and every node across the network executes these same instructions. It solves a real problem, but it's very inefficient. In contrast, Mina zkApps use a different model. We have off-chain execution, and the smart contract runs in a web browser using WASM. A user will execute one of the methods on the smart contract, and private data that a user inputs into a method will end up, the smart contract will generate a zero knowledge proof, which gets sent to the blockchain, along with a list of state updates if that blockchain is proven to be correct for that particular zkApp account. So this gives us a few advantages. We achieve blockchain scalability through succinctness. We have that 22 kilobyte proof that proves consensus. So that source of truth always remains very small, which of course is the key aspect of a blockchain. We also get user privacy through zero knowledge. Because the smart contracts are running off-chain in a user's web browser, any data that the developer wants to keep private, they can specify private data arguments that will be input into the smart contracts that the blockchain will never see. And then we also have the opportunity to have unlimited off-chain execution. So zero knowledge proofs have a unique characteristic where no matter how large your computation is, whether it's very quick or very long, doesn't matter, because that zero knowledge proof that results from running that function will always be quick to verify. So we send that zero knowledge proof to the chain, and the chain can always verify that very quickly. So how does this work? A zkApp consists of two things. So just as a matter of terminology, we use the term zkApp to talk about the UI, the user interface, and a smart contract. And the smart contract is written with SnarkyJS. So Brandon, in his portion about SnarkyJS, that's what he's going to help people get started with. So how does this work? When a developer writes a smart contract and they run their build in their application, it generates a prover function and a verification key. The prover function runs locally and generates a zero knowledge proof. So this is what's going to run in the user's web browser when they're interacting with the zkApp. And then it also generates a verification key that they deploy to the network. So if you're a developer and you update your application logic, you will build again and generate a new verification key that you deploy to the blockchain, and then you have a new deployment. So any transactions will then have to pass the verification key, whatever at that point in time. So again, deploying a verification to the chain creates what we call a zkApp account. This is exactly identical to a Mina account. However, when the verification key exists on it, we call this a zkApp account. And transactions they have to be valid, as mentioned, for the verification function, and they will only be accepted by the network if they are, in fact, appropriate for that zkApp account. And that's how we can ensure that even with off-chain execution, that we know that zero-knowledge proof that the user has run the expected computation. And if they haven't, the transaction will simply be rejected by the network. Okay, so in a little more detail, let's talk about how a smart contract works. A smart contract, keep in mind we're running in the user's web browser, accepts a few different things. We have method arguments, which can be private data. And then we also have some smart contract states, which is public data that lives on the blockchain. And this generates a couple outputs. So updates to the state of the smart contract, that public state that lives on chain, and updates to the state of the world. So maybe you sent Mina and you changed somebody else's balance. And one really important thing to mention is we have what are called preconditions. So as a developer, if you want an action to only occur, such as sending funds from account A to account B after a certain block height, you can specify certain preconditions, and you can specify those based on either something that's account state related or network related that way too. Okay, and smart contracts, the really cool thing about smart contracts on Mina Protocol is they're written in TypeScript. So you have the opportunity to use VS Code, NPM, Prettier, a whole bunch of technology that you're already familiar with. And you can download, if you want to get started today, you can download our zkApps CLI. So for Brandon's presentation, just keep in mind that if you can run 2 commands and have a project set up and be ready to go with your projects. And then I want to pass to Evan to talk about the bridge.
Awesome, thank you. So yeah, I'm going to talk about a part of Mina, a really cool component called the zkBridge. So this is this question of, okay, we have this cool zkApp functionality. How can we make this useful and available on all these other platforms? Because we have very efficient zero-knowledge proofs. Maybe there's some way we can get that to other chains, which seems like it would be a pretty cool thing and valuable to everyone else on those other platforms. So the answer to this we have is this zkBridge, which leverages Mina's succinctness for a cryptographically secure bridge to Ethereum and other chains. The idea here is that, so we have for Mina this recursive zero-knowledge proof that updates every single block and says the current Merkle root of the Mina ledger, the current state of the Mina ledger is correct and has valid consensus information backing it since the beginning of time. And you can check that zero-knowledge proof and know that you're looking at the correct state of Mina. And what's cool is this is lightweight enough that we can run that itself inside of an EVM contract. So that's as if we have a full node of Mina, in a sense, running inside of a smart contract. And what's cool then is that anybody can then update that smart contract because the smart contract itself can run Mina's consensus and strongest chain rule. So it's like this decentralized way of having a contract that contains the strongest state of Mina at any time. And then what's cool is that with one bridge update, so one verification of a recursive zero-knowledge proof, you can move over all the state that has changed on Mina since the last time you updated the recursive zero-knowledge proof on Ethereum. So if that made sense, great. If not, we're going to run through an example, so you'll see how it works in detail. The The example we're going to go with is, let's say we wanted like a private proof of attendance. So this is like, I think there is actually proof of attendance protocol, which is super cool. This is like a private version of that. And we want to make that work between Mina and Ethereum. So the way this can work is, first what happens is a developer is going to write this program called was@Ethereum that runs on Mina. And a user can create a new zkApp account on Mina with the verification key for the app the developer wrote. Great so far. And the data field on this is all zeros because we haven't filled it in yet, but we'll fill it in a second. Next that happens is user submits a zero knowledge proof that says, okay, like in this example, I have an identity. That identity has been verified by a third party. Like I went to like the DMV website and like looked at that page and it was good, as well as an actual valid ETHAmsterdam pass and they matched. And then what I can do is I can make a zero knowledge proof of that and submit it to Mina. And then that allows me to update the data fields on Mina and the zkApp in this example to my Ethereum public key. So note that if I didn't have a valid zero knowledge proof that contained this private information about my attendance, I would not be able to update this zkApp with that public key and it would just be all zeros still. But because I was able to add my Ethereum public key into the Mina account. Great. So what's next is that we have to get that Mina state account onto Ethereum itself. And for that, we're going to look at what I've called here like the Mina Bridge account on Ethereum, which contains as its data, not the whole tree actually, but just the Merkle root of the tree for Mina's ledger. And then an operator, someone who wants to update that account in a decentralized way, can send over that Merkle root and consensus information back to Ethereum. And if the consensus information in that new proof is actually stronger than the proof that was already on Ethereum, it updates to that latest proof and latest Merkle root. So after this, our Merkle root that happens to contain the zkApp, which happens to contain my Ethereum address, is now on Ethereum. Great. So after that, so in this example, it's like a DAO for people that happen to attend here. What we can do is someone can attempt to register, and the registration process includes a Merkle path from the Mina Merkle root in the Ethereum smart contract down to that account that contains that Ethereum public key. And the user can prove that that was included, that corresponded to like the verification key that actually corresponded to the zkApp that was written, and that they actually have the private key that can make signatures which correspond to that public key. So in any case, with this, they can register themselves into a DAO using a zk proof that they have the rights to do that. So I hope I didn't go to that too quickly, but that's basically the flow that one can imagine for how you can write something on Mina that takes advantage of zero knowledge proofs. And then from Ethereum or other chains, you can then access that as part of your application. So there's a bunch of possibilities one could imagine with this. You could build a private DAO if you wanted to. You could pull real-world data into like Bootstrap, more DeFi things. You could build NFTs that have some cool zk properties. One in particular I think could be cool is like a collection where each person can own at most one NFT. So like if you have a bunch of capital, you're still limited in how much you can take from the collection. You can put like anonymized proof of on-chain information for Ethereum or other chains. You could build zk-powered games, like Battleship is like a good one with some privacy element. I think another thing that potentially will be cool, at least interesting, is making it possible to actually move private enterprise data onto public chains for that interoperability without losing the privacy aspect for those. As well as one thing I think is also very cool, it's very easy to spin up a zk rollup in this framework because the cryptography is done. You just kind of have to like write the recursive step for your zk rollup and then do that off chain and then submit a big proof back to Mina. But that's all I have for this part. Thanks. Yeah, I'll hand it off to Brandon.
Hello. Cool. Okay, I'm going to talk about SnarkyJS. So, SnarkyJS is a toolkit SDK that lets you build zkApps, and you use TypeScript. And so, because it's TypeScript, as Jason mentioned, we can use open technologies. The actual execution happens in the browser or Node.js, typical runtime environment. You can use existing JavaScript and TypeScript libraries and tools. That means you can also use like VS Code, and you get all the benefits that you get from VS Code, all the IDE support of just JavaScript and TypeScript that thousands or millions of person hours have been poured into, you get to use that. So cool, SnarkyJS. I know like maybe some of this stuff seems really scary after we saw the details of the architecture and the bridge example, but the code is really not scary. I will prove it. So in a moment. First, so I want to talk about like the base sort of unit of data in zero-knowledge programming, field element. So a field element, it can store a number that's almost 256 bits in size for the field that Mina uses. You can think of it like a uint256 in Solidity, but it's just slightly smaller. For those that are like zk like crazy people, the field in the field type in SnarkyJS, this is the base field of the pious curve and the scalar field of the Vesta curve in Mina's pasta curve system, unless someone on my team corrects me and I got those mixed up. But but if you don't know what I just said, it really doesn't matter. Just think of it like a 256-bit unsigned integer. So in typical programming of TypeScript, like you might sum two numbers by creating a local variable and then writing the integer literal 1, the symbol plus, and then an integer literal 3. Or I guess, I don't know, a numeric literal. I don't know what you call them in JavaScript, but those are JavaScript numbers. In TypeScript, we can't override like numeric literals. So we have a little bit of like wrapper glue to sort of tell the SnarkyJS engine that we're using field elements. So this is how you would add 1 and 3. And this is a little cumbersome, so there's some syntactic sugar. Anywhere that like it's unambiguous what you mean, the methods accept like a numeric literal, a string literal that corresponds to a number, or another field element. So it's just like a little bit slightly more characters than 1 plus 3. Cool. So there's other built-in types besides fields. Here's a few of them. So besides field, bool is one, and this is just a field that's constrained to be 0 or 1, but it has a bunch of helpful methods on it for things that you might want to do with, bools. We have unsigned integers of sizes that are normal for machine, like computational machines like this laptop. And then public key, private key, signature that for Mina's system. We have a Schnorr signature. And then some other cryptography things, group scalars. The scalar is the other field in the recursive pasta system. Again, it doesn't matter if you don't know what I'm talking about. All of these have built-in methods on them, and because it's TypeScript and because we have VS Code and other IDEs like that, you can just import one of these things, create an instance of it, and then write like your variable name dot, and then autocomplete will just help you explore the SDK. You can just write functions. So in TypeScript, you write a function like this. You can give your parameters types, and you can return a type. And here we are adding 1 to x and then doubling it or multiplying it by 2. Just like in TypeScript, I mean, it is TypeScript, but just to really show you, we can take a part of that expression and assign it to a local variable. So it's really normal programming. I'm harping on this because if you attempt to program using any other zero-knowledge proof framework, you will miss normal programming, I think. So let's go through a simple hello world, okay? A hello world smart contract. So we're going to write a smart contract that has a single piece of state, a field element that we call x, and we're going to constrain we're going to have one method called update, and we're going to only allow update to replace x with its square. So just to give you a sense of what I'm talking about. If we start at 3, the only update that's valid is 9. And if we're at 9, the only update that's valid is 81. So if we start with 3, update it to 9, and then we try and update it to 75, actually the proof won't even be created. But if you try and send something messy, or if you try and spoof the chain, it'll also reject your transaction. Cool, so let's write it. First, we extend smart contract. You just write a class, extend smart contract. We make the state by adding a member variable with some decorator stuff. This line of code's a bit confusing, I suppose, but it's doing so much for you that it's amazing. What this says is X is a piece of state that lives on chain, and its type is field. And you can actually use any type that's built out of field elements here, which I'm not going to show in this slide deck, but you can see in our examples. And this is public and on chain. So we're going to say what happens when we deploy. Okay, so by default, there's some things that happen, but we want to override the default by setting it to 3. So we call super.deploy with the input, and we set X to 3. Okay, so now the actual update method. Let's just speak about methods, I guess. Smart contracts have multiple methods, or they can. This one only has one. And these are the things that you can do to a smart contract. So this is like the functions you can invoke on it. And Jason was mentioning this, but I'll say it again with the code. The state, the member variable there, that's public. That's on-chain. Anything you store there is publicly readable. If you store a hash, then only the hash is publicly readable, but it's public. The arguments to the methods are private, and they are only, they're only visible on the user's machine. And if you don't put them in some public state, they will just remain private. In this case, we are putting it into public state. So you can see that on the third line of that method. So the other thing that's happening here is on the first line of the method, we're calling this.x.get, which fetches the current state of the zkApp from the chain. And there's some magic that happens that Gregor can tell you later, where this isn't actually asynchronous because we sort of get it before this runs. But the point is, there were a couple reasons we did that, but a nice benefit is you don't have to even worry about async await. You can just write normal, plain, sequential programs. So that gets the state, and then we do this thing on the second line where we add an assert. We assert that the square of x is equal to the thing that we passed in. And this isn't just something that, I guess typically when you have assertions, you put them in there for sort of your sanity as a developer. But this is actually something that is sort of part of our smart contract. And the thing that actually happens when we run this, again, this is Jason talked about this in the abstract. I'm going to talk about it in the concrete. What we do when this executes is we produce a transaction that says, it has a proof in it that says we ran the code in this update method with some private arguments. And the result of that were the following instructions that get sent to the chain. In this case, set x to be 9. That's the instruction. And it assumes a precondition that x is 3. So that gets baked in to the smart contract. If the transaction is sent when the state is not 3, then this will fail, which is what we want, because we only want to update it to its square. Okay, so this is kind of what smart contracts look like. This is a very simple one, but there's member variables, which you can use for state, public state. You can override the deploy method, and you can add methods with this @method decorator that correspond to the specific, updates that you want to perform on the to the network, I guess. Cool. So now to test this, there's, I guess, a lot of things you can do. The thing that we recommend that you do for this hackathon, because it is the most easy to use at the moment, is testing locally. So here's an example. So what we're doing here at the top, we're grabbing an instance of this local blockchain you can kind of think of this like a sandbox VM. Literally, it's like part of Mina that's compiled to JavaScript. So it is you know, accurately emulating the real blockchain. And then we send a transaction using account 1 is the one who pays the fees for the transaction. So you have a private key there, and then in there we're only deploying the smart contract in this example, and then sending. That's that .send at the end. So and then you know we can also at the top here we can send an update. We can update it to 9. And then afterwards we can get account states and then you know print them out or you know check them against something else in like jest in a jest test. If you're a web programmer, you'll know what that means. Or you could just put that in another executable for your testing purposes. Yeah. So I also want to just show. Evan touched on this, but rollups. Here's a rollup, and it's like 10 lines. It's probably like going to be 50 lines if you actually get, you know, unwind the ... dots, but like it's 50 lines, a zk rollup. This API we have not fully wired in, but I just, you know, thought it would be really cool to show. So, you know, at proof system, you extend proof to make a custom proof that's not, you know, like this proof isn't actually on chain. We like create the proof and then send the proof through our smart contract on chain. So we extend something different. And then you know, maybe you're like, you deposit money into the rollup. You can like send transactions between accounts within this rollup environment. And then you can merge proofs together. Yeah, this is pretty cool. The one thing, I also want to just touch on this. For people who have tried to use recursive zero-knowledge proof programming before, it's probably not a large number of people, but if this is one of you, you have to flip between like the two different fields every time you recurse, and this is actually like really complicated and annoying to write code for. And the Pickles recursion execution engine in Mina like double flips for you. So all this means is like you really only have to think in one field, which is really something that makes your life easier. So that's that. How do you learn more? Well, you can go to these places. So the docs, the Discord. You should also look for people with these hoodies, most of which are members of either the Mina Foundation or O of One Labs, and we can help you, you know, understand things. Oh, and the other thing I want to mention, we are like in real time getting like we have successfully deployed zkApp transaction or like zkApp smart contracts to a live test network and interacted with them in a live network environment. In constrained conditions, and we are actively at this second working on making those constrained conditions less constrained. So if you are at a point in your hackathon project where you are like, I'm done, I'm tested, it's great, and I want to hook this up to a live network, then you should look for people in these hoodies, and we'll point you to the person in the hoodie that you should talk to. Yeah. So that's that. We have time for questions, I think. So. Yeah. Do we want to mic the question answerers?
I can just talk really loud.
I'll repeat your question. Okay.
Well, so given the like constrained size of the chain, like how do you infer the state of like any particular contract at a given time?
Yeah. So the question was, given the constrained size of the chain, how do we get the state of anything that we care about? Okay. So there's like a lot of nuance and a lot of different answers. So I will answer the question that I think that you're asking, which is, and you tell me if I'm answering the wrong question. So this 22 kilobyte number, actually on our homepage, there's like a superscript, and you can click on it, and it's a blog post that I contributed to that explains in detail exactly what we mean by these 22 kilobytes. If you read those details, you'll see there's a proof that's like 1 kilobyte-ish. And then there's like a bit of metadata and a Merkle path to an account that you care about. And if you, so how do you get the state that you care about? You ask a node that has some state. And I just want to highlight the nodes that are participating in consensus and mining blocks, they have the current state of the world. You need that to produce blocks. You do not need that to be like a full node in the security sense, but you need that to produce blocks. So there are a lot of nodes in the network that have the current state of all the accounts. There is no node that's needed for consensus that has ancient archive state. As Jason was saying, there are some that do because sometimes people want it, but it's not needed for consensus. But it is needed for consensus to produce blocks to have that state. So, sorry, this is a long-winded answer. But you just go and ask those nodes for the state in the same way that like you go and ask an arbitrary Ethereum node for like your account and it gives it to you. It's the same thing.
Do you think there's any limitations with zero-knowledge proofs? Because I've seen this, so there's a verification key as well. I guess also there's some constraints that need to be met for the proof when it comes in as well. It goes into it. Do you think if I had like a really big program that I was running, do you think that maybe I might be, you know?
Yeah. The question was, are there constraints on like how big the program is, given that there's this fixed verification key? And naively, the answer is yes. There's a fixed maximum size that your computation can be per verification key. And this is true. However, because we have recursion, we can just recurse and loop a bunch of times and do very complex things that don't fit without recursion into one proof. I guess I'm realizing that might not make sense to people, but it is true, so that's the answer. Yeah.
Yeah, so do you use some Snark theme algorithm that like doesn't require a setup for each and every new circuit?
Yes, very good question, and I wish that we had mentioned it in the talk. I'll mention it now. The Mina zk snark does not have a trusted setup. It is a false god that I don't know what the term is. It is untrue that like snarks imply trusted setups. Some people have this meme. It's not a real thing. Our snark does not have a trusted setup. And therefore, and it's universal. And you know, one of our cryptographers can correct me if I say this wrong, but that means that we can basically change what the circuit is at runtime and in Mina's case, we can recurse arbitrary new circuits into the main Mina circuit. So all this means like when you are writing a zk app, when you're writing a smart contract, you can deploy an arbitrary new circuit and it gets folded into Mina and there's no trusted setup. There's no setup.
But is there no trust? So
there is full trust and you trust no one because the cryptography works without trusting a setup.
No, I mean you've said that your setup is not trust. Like, did you have like a ceremony and
no, Mina did not have a ceremony because Mina's snark does not require a ceremony. Yeah,
okay,
it's more.
So it is safe.
It is safe, and the cryptography is even safer than. I think ceremonies aren't that like untrustworthy personally, but Mina didn't have any ceremony, and so it's even more safe than if you did. So yes, it's safe, good cryptography. I mean, it's newer cryptography, so sometimes that scares people. But we have very smart researchers and research papers and audits and you know, people reviewing stuff. So I think it's fine. Okay.
So when you said strongest chain, or one of your friends said strongest chain, I guess that relates to some mechanism like proof of stake.
Yes. Yeah. So actually, the recursive zero-knowledge proof way that Mina compresses the blockchain is sort of orthogonal to the consensus mechanism. And actually, an early test version of Mina we implemented proof of work because it was easier, but we didn't want to release that. So it's proof of stake because we chose that we wanted proof of stake. And specifically, the consensus mechanism is a variant of Ouroboros, which is called Ouroboros Samasika. And you can look online and read about it. There's a bunch of talks and papers and things. Ouroboros was originally created by the IOHK Cardano folks, and Mina tweaked some things to make it work in a succinct environment. Yes.
How that connects on ERC 721 to your smart contract?
Say that again. How do you connect? What?
ERC 721, like an NFT.
Like an NFT. Yeah. So yeah, I think so. One thing I'm really excited about is bringing Mina proofs to Ethereum through the bridge as non-transferable NFTs. I think that's like an awesome, cool thing. That like framework for building that has not been written. It would be a really good hackathon project. I'm going to contribute to judging on one of the projects, and if someone implements that and it works, like I will vote for that project. I mean, like yeah. So the answer is like. You should build that? I don't know. The bridge, the zkBridge isn't deployed yet. Right. So so you can't actually run it yet on on Ethereum, but you can still build the infrastructure so that right when the bridge is deployed, we can do that sort of thing. So I hope that sort of answers your question.
So sorry, could you repeat the question?
Sorry, the question was, how do we interact with ERC 721 NFTs in Mina? And I guess with Mina. I answered one half of that, which was how do you output them? And then the other half is how do you input them? And that is also part of a bridge that doesn't yet fully exist. But also, if you build part of that, it would be a good hackathon project. And you can talk to, if you feel like you have enough in your brain to understand how to build something like that, one of us in the hoodies can help you understand how to, do that as a project.
So another question. So like, if do I understand correctly that the bridge basically, like you could use it to reduce fees from instead of verifying the proof on the Ethereum chain, you have to just verify the Merkle path, right? So that's the gas optimization that you could do, right?
Well, you have to, yes. Well, someone is verifying the Mina proof on chain, like whoever is updating the bridge. But yes, once it's already there, it's just a Merkle lookup.
Okay.
Right?
Yes. And
okay.
Does so is it supposed to is the Mina are you supposed to update the bridge on the who runs the bridge?
Yeah. There are a lot of entities that could run that, post those updates. I bet Evan has thoughts on.
The plan is it'll be decentralized. Anyone can be an operator, and if you want to help us test being an operator, then you should also reach out to us.
I'll repeat on the microphone. The plan is that it's decentralized. Anyone can be an operator, and Mina Foundation, as represented by Evan, says that they want. I'm part of Ov1 Labs, separate company. They want to help people be operators. If you want to be one of those operators, you should talk to someone in a hoodie, and we'll help you learn about that.
So how does the fee system work?
The question is, how does the fee system work? I think Jason mentioned this, but because all transactions in Mina, and actually even before zkApps, this is how it worked. They all correspond to verifying a proof. They're all the same price. So they're all the same price. I guess there's some nuance where there is a way to build zkApps such that a single method, that you write in SnarkyJS actually compiles to several transactions, and then you pay per extra transaction, but it's a fixed gas cost per transaction. And that means you can do some crazy computation which the user will pay for, because when they're using your application, they'll perform that computation. But you don't pay for it with gas.
I'm curious, if I have, let's say, 10 pending transaction, and every one of the transaction wants to interact with one smart contract, does it mean just one transaction will go through and the 9 are invalid because the one will change?
Good question. Yeah, if you build your state machine in such a way, like this example, where there's like a sequential ordering of updates that needs to happen, then there's a race, and whoever gets there first wins, and the rest are invalid. But you can design your state machine, and there are a lot of ways to do this in zkApps and like conceptually. You can design your state machine such that updates can be reordered, and that is what you should do if you want that property. But it means that you have to think a little bit harder about how you design your smart contract. Please.
So that's a really great question, because with the off-chain execution model and off-chain storage, which is in progress as far as making it elegant, there are a couple different approaches to that also. The preconditions, we mentioned the network preconditions and account preconditions. I believe that we can work on that to create very elegant preconditions that might be tailored to a specific app that could really help address that. And then when we have rollups as well, and actually one of our zkApp builders in our recent program has started a rollup, that would have another opportunity to provide sequencing as well for a particular app and use case.
Cool. Any more questions? Go ahead.
I think we need to store more complex data on off-chain because this is not a primitive type. What if we lost off-chain data forever?
Yeah. So the question was, sometimes we need to store things off-chain because they might be more complex. I should just mention, because we didn't mention this, in the current testnet, I guess this isn't set in stone, we're thinking that each account has 8 field elements worth of storage on-chain, which is a very small number. So a lot of times you'll have data that isn't on-chain. And the question was, what happens if that data gets lost? And the answer is, your application won't work, but Mina will still work. So it's up to you as an application developer. There's a couple answers to this. The current answer is, it's up to you as an application developer to solve this problem in the way that you think is important for your application. So the easiest thing to do is just like have a file that has the state in it. And you can think of this as like a single sequencer. And this is, from my understanding, how basically all the L2s work right now, that people have a lot of capital on. And people seem to be OK with that. You can do something that's more safe and decentralized by having like a Tendermint chain that keeps track of the state, or you can have the Merkle tree in like some flash drive that you like that you make a copy of and hand to your friend. So you can do anything for the state, and as a SnarkyJS toolkit developer person, architect, whatever I'm called. Myself and Jason and a bunch of other people, we will be working on ways to make to solve this problem in sort of more cookie cutter ways, so it's easier for application developers to make that decision, and they can just kind of take something off the shelf. But right now, it's a little bit more manual. Yeah, hopefully that makes sense. Cool. I think we're out of time, actually, so thank you. Remember, you can just, anyone wearing these colored hoodies and or these links, you can come and ask other questions or whatever. And please build stuff. There's prizes. I think someone's going to announce that. So, yeah. Thank you. What's our prizes? We have prizes. Okay.